Hey you guys, this is Mr. Millings, and in this video we are going to learn how to use the density formula along with the idea of water displacement to determine the initial volume of water that is in a graduated cylinder prior to some object being placed in it. And so if we read this question here, it says to determine the initial volume of water, prior to the tungsten being placed inside the graduated cylinder. So we have a graduated cylinder here, and in this graduated cylinder there's some water. And also in this graduated cylinder we have a metal, in this case tungsten. And so let's think about this. If we place an object in a graduated cylinder that is filled with water, the water level is going to rise. And if we remove this object from the graduated cylinder, then the water level is going to decrease. And so what we're asked to figure out is what the initial volume of water was before we placed this object in here. And so let's think about this. How are we going to calculate the initial volume? How do we get V naught? V naught means initial volume. If we want to figure out the initial volume here, what we'll have to do is we'll have to take the final volume of the water that is in this graduated cylinder, and we're going to have to subtract the volume of the metal from it. In this case, the volume of our tungsten. The chemical symbol for tungsten is W. So if we figure out the volume of our tungsten here, what we can then do is subtract that from the final volume of the water that's in this graduated cylinder, and that will give us the initial volume of the water that was in this graduated cylinder prior to us putting the metal in here. And so if we take a look here, we have a triple beam balance with our tungsten that has been placed on it, and we can figure out the measurement of mass using the triple beam balance. And so we also have a table of density values, and if we take a look close, we can see that the density of tungsten is right here. It's 19.600 grams per cubic centimeter. And so what formula do we know uses D, or density, mass, or M, and V for volume? Well, that's going to be the density formula. Density equals mass over volume. And so we can figure out the density of tungsten by looking at the table. We can also determine the mass of this tungsten by looking at our triple beam balance. And so what we can do is we can solve for the volume. We can calculate the volume of the metal that has been placed on this triple beam balance. And once we figure out the volume of this metal, we can then plug it into this formula right here. The initial volume of the water will be equal to the final volume in the graduated cylinder minus the volume of our tungsten. So let's go ahead and figure out the volume of our tungsten. Well, we're going to have to manipulate this formula and solve for V. So let's go ahead and do that. If we know that density equals mass divided by volume, we want to get rid of the fraction here, so we're going to multiply by V on both sides. V now cancels, and what we're going to end up with here is volume times density equaling mass. But we want to isolate V. We want to get V all by itself on one side of the equal sign, so we'll divide both sides by D. D now canceled, and so to get the volume of this metal that is on this triple beam balance, we're going to take the mass and divide it by its density. So here's our formula to figure out the volume of this metal. And so now that we've figure out the formula we're going to use, let's go ahead and figure this out. To get the volume of our tungsten, to get the volume of the tungsten here, we'll take its mass and divide it by its density. So what is the tungsten's mass? Well, let's take a look here. If we take a look close at our triple beam balance, we know with 100% certainty that the mass of this is going to be 410. Right? And if we take a look at this rider right here up close, it's not quite 411. So we know with 100% certainty that the mass of the tungsten is 410. If we take a close look, grams, right? We know with 100% certainty it's 410 grams, but take a look at this rider right here, 410.1, 0.2, 0.3. 410.3 grams, and in an earlier video on measurement, we learned that we have to take our measurement one significant figure past the level precision of our instrument. Our instrument here is precise, it looks like, to the 10th of a gram, so we have to estimate one significant figure past that. We have to estimate what this is, and we see here it's just a hair past the 0.3 line, so we'll call this a 1. So the mass of the tungsten that is on this scale right here, or this balance right here, is 410.31 grams. 410.31 grams. So what is the density now of tungsten? Well, if we take a look, the density of tungsten is 19.600 grams per cubic centimeter. Take a look at what happens now. We have grams in the numerator and grams in the denominator. That is why it's important that when we're solving for volume, the mass has to be in grams and the volume should be in grams per cubic centimeter. So these guys can cancel out right here, leaving us with centimeters cubed as our unit of measurement for volume. And so now we'll put this in our calculator, 410.31 divided by 19.600, and we're going to end up with 20.93. So the volume of this piece of tungsten here is 20.93 centimeters cubed. Now keep in mind that a centimeter cubed is the same thing as a milliliter. They're identical. They're the same amount of space. We typically will use centimeters cubed though for solid objects and gases sometimes, and we'll use milliliters when we're referring to a liquid. But understand that a centimeter cubed is the same thing as a milliliter. So we can say that this is the same thing as 20.93 milliliters as the volume of our tungsten right here. And so now that we know the volume of our tungsten, we can now plug that into this formula right here and solve for the initial volume of the water. Keep in mind that the initial volume of the water is going to be the final volume of the water minus the volume of our tungsten. So what is the final volume of our water? Well, let's take a look at our graduated cylinder. In our graduated cylinder here, we have to figure out the increments by which this graduated cylinder is graduated. So if this is 5 milliliters here, and this right here is 10 milliliters, and there's 10 lines in between, then each one of these lines here is going to represent 0.5 milliliters. So this graduated cylinder here is graduated by 0.5 milliliter increments. And so let's get the final volume here. To get the final volume here, we see that this is 40, 40.5, 41, 41.5, and it's not quite at 42. So we're going to call this 41.8. We'll call the final volume 41.8 milliliters. So the final volume of our water that is in here is 41.8 milliliters minus the volume of our tungsten, right? The volume of our tungsten is 20.93 milliliters. And so the initial volume of the water that was in this graduated cylinder prior to us putting the metal in here was 20.9 milliliters. And now keep in mind that when you're doing this problem right here, we'll have to pay attention to the rules of significant figures when we add and subtract, because this measurement here only has 1 decimal place and this has 2 decimal places. We have to round our final answer to the smallest or lowest amount of decimal places in the measurements that we added or subtracted. So because this is 1 decimal place, our answer here had to be 1 decimal place. So the volume of the water that was in this graduated cylinder prior to us putting the metal in here, it appears to be 20.9 milliliters. So if you like what you see, go ahead and click that little bomb in the bottom right hand corner. That will subscribe you to my channel, and feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.